So far, when dealing with partial fractions, we have been assuming that everything is going to be factorable, that we can always factor down to linear terms. However, that's not always true. So now we'll discuss the case where that's not. In general, ax squared plus bx plus c in the denominator is going to correspond to a separate kind of term in the partial fraction decomposition. It's going to look like ax plus b over ax squared plus bx plus c. Essentially, I'm going to need to go down by 1 degree. So in the top, I'll still need an x term. I'll still need something linear. And so anytime you have something not factorable, this is what it's going to look like in our decomposition. We'll start with this example. And if I look at the denominator, we do need to factor it. The first two terms have an x squared in common, and I'm left with x plus 1. And the second terms have nothing in common. We can then see that I can factor this into x plus 1 times x squared plus 1. And x squared plus 1 does not factor any further. Therefore, this is an irreducible quadratic term. When I set up my partial fraction decomposition, the x plus 1 just gets an a. And then the other term, the irreducible quadratic, is going to correspond to bx plus c. We can then multiply by the denominator. On the left, I have x squared plus x plus 2. On the right, a times x squared plus 1. And then plus bx plus c times x plus 1. We may be able to simplify things by saying let x be equal to negative 1. On the left, I would then have 1 minus 1 plus 2. On the right, that bx plus c term would cancel, and I'm left with 2a. Therefore, a is equal to 1. However, there's nothing I can stick in to make the a term cancel and not the bx plus c, so we're going to have to use our other method here. When we multiply out the right-hand side, I get ax squared plus a. I then have bx squared plus bx plus cx plus c. Grouping things, I have an a plus b, x squared. For my x's, I have a b plus c, x. And then my constants are a plus c. On the left, the coefficient in front of the x squared is a 1. On the right, it's a plus b. The coefficient in front of x on the left is a 1. And on the right, b plus c. My constant term on the left is 2. And on the right, it is a plus c. Luckily, we already know that a is equal to 1. Sticking that into my first equation shows me that b is equal to 0. I can then use that in my second equation and get that 1 is equal to 0 plus c, so 1 is equal to c. In this case, we only needed 2 equations, but that's fine. The third one could just be a backup. We can see that a is 1 and c is 1, so 1 plus 1 is 2. That is a nice way to check your work. Integrating this, the integral of 1 over x plus 1 is ln of x plus 1. And the integral of 1 over x squared plus 1 is inverse tangent. So arctan of x. And then plus c. Here's our next example. And this time we can see our denominator's already factored for us, so we don't need to factor. Here, the first term is an x minus 4 squared. And our rules say we would need an a over x minus 4 plus b over x minus 4 squared. The x squared plus 3 term would then need a cx plus d. And now we can solve this. If we multiply by the denominator, we have x squared minus 29x plus 5. is equal to a times x minus 4x squared plus 3 plus b times x squared plus 3 plus cx plus d times x minus 4 squared. If I let x be equal to 4 on the right, 16 minus 29 times 4 plus 5, or rather on the left, we end up with negative 95. On the right, the a and the cx plus d term cancels. I'm left with 16 plus 3 times b, which is 19b. And then dividing, negative 95 divided by 19 gives me that b is equal to negative 5. We then need to use our other method, and when we multiply out the right-hand side, I'm left with ax cubed plus 3ax minus 4ax squared minus 12a plus bx squared plus 3b. And then the last term is a little more difficult because we do need to FOIL everything out. We will end up with a cx cubed minus 8cx squared plus 16cx plus dx squared minus 8dx plus 16d. Grouping, I have an ax cubed and a cx cubed. For my squareds terms, I have a negative 4a plus b minus 8c plus d. For my x terms, I have a 3a. I also have a 16c and a minus 8d. And then finally for the constant terms, negative 12a plus 3b plus 16d. We can now set things equal, and we'll take these one by one. If I look at the x cubed term on the left, there's not one, which means it's 0. On the right, we have a plus c. On the left in front of the x squared, I have a 1. On the right, negative 4a plus b minus 8c plus d. The x term on the left is a negative 29. On the right, 3a plus 16c minus 8d. There's a 5 as a constant term on the left, and on the right, minus 12a plus 3b plus 16d. And we would now need to solve a system of equations. Even though we know what b is already, that doesn't simplify us enough to finish getting this. So therefore, we would need to simplify this systems of equations and solve it, and then we would have our partial fraction decomposition. We will not go any further here. I mainly just wanted to set this up and show you the process.